Hi, what I'm going to do today is a problem for momentum in 2 dimensions. So instead of just everything happening in a line, now we've got things in 2 dimensions, up, down, and left, right to take care of. It's still conservation of momentum though, so still same thing happening. Our problem is very exciting globs of clay. A 35-gram glob of clay is moving at 1.8 meters per second at an angle of 25 degrees above east, and it collides with a 15-gram glob of clay moving at 2.5 meters per second at 15 degrees south of west. What is the speed and direction of the combined glob after the collision? So we have 2 globs of clay, and then they're going to collide, stick together into a bigger glob. And we want to know, where's that bigger glob going? So for momentum, we need to have an initial picture and a final picture. We have one moving at an angle of 25 above east. So there's east, 25 above. So my first one is moving something like this at an angle of 25 above east. And then we've got the second one moving at 15 degrees south of west. West, 15 degrees south. So the other one is moving something like this. Okay, they're not exactly, they shouldn't be pointing exactly at each other. Close enough. 15 degrees south of west. All right, and then what do we know? For the second glob, our mass is 15 grams. That needs to get converted to kilograms. 0.015 kilograms. Its initial velocity is 2.5 meters per second at 15 degrees south of west. Our first one is a mass of 35 grams. 35 grams, so that's 0.035 kilograms. And here we have an initial velocity of 1.8 meters per second at 25 degrees above east. So that'll be north of east. We want to know what is V final for the combined glob. So these two are going to smash together, and then they're going to stick together. So we've got this, so here let's do A like that, and B like that, and we want to know, where's this thing going? What direction is it moving? How fast? So that's what we're going to do. Now, conservation of momentum in 2 dimensions is exactly the same as conservation of momentum in 1 dimension. We just separate it out. Do the x's separately from the y's, just like we did with forces. So back in forces, we had this table of the x components and the y components. We're going to do something similar here, where we just say, okay, I'm only dealing with horizontal motion to start with, and then I'm only going to deal with vertical motion for my second piece. The equations that we're using, it's still initial equals final, but we're going to treat the 2 directions independently. And boy, do the subscripts get confusing here. So be really careful with your subscripts. The initial momentum horizontally in the x direction is equal to the final momentum in the x direction. Initial momentum in the y direction equals final momentum in the y direction. All right, so let's do them one at a time. I'm just going to start with the x direction. P initial x equals P final x. Well, I have 2 objects initially, so I'm going to have mass of A times V initial A in the x direction, plus mass of B, V initial B in the x direction. So that's the momentum of my 2 objects. That has to equal the final momentum in the x direction. Well, now it's just 1 object. I can call it 1 object of a combined mass. Mass of A plus mass of B times the final momentum in the x direction. So there's my equation for the x direction. And what do I know? Well, I know my mass. I know I can figure out, I guess, got to do some trig. I know that. I can figure that out. I know that. I can do that. All right. We have to do some trigonometry to figure out what the initial velocity is for these 2 in the x direction and the y direction. You've done this a lot by now. So in the x, for A, I need some space. Well, I'll do it here. For A, we have 25 degrees here, and our initial velocity was 1.8 meters per second. This is going to be my y direction component of that. This will be my x component. So the x component is adjacent to my angle, which means that I want to use the cosine component for x and the sine component for y. If you do that, you end up with, let's see, what do we end up with? Horizontal of 1.63 meters per second, vertical 0.761 meters per second. And I'd better be careful here. Are these both positive? Are they negative? Are they one of each? This one is moving up and to the right. Up and to the right. Up means a positive y, so I have a positive here. Right means a positive x, positive there. How about this one? So we're given 15 degrees, and our initial velocity was 2.5 meters per second. Here, this is my y, and this is my x. Again, given this angle, my x is my cosine component. So v initial x and v initial y. V initial x was 2.41 meters per second. V initial y is 0.647. Again, we have to take into account direction. Momentum is a vector. We're going down and to the left. Down means negative y. Left means negative x. Okay, now I can do this. For now, all I care about is the x direction. So I'm going to be using the 1.63 and the negative 2.41. The mass of A, 0.035 times V initial A in the x direction. Here's A, V initial, x direction, plus 1.63, plus the mass of B, 0.015 times V initial BX, B, V initial, x, negative 2.41, equals the mass of them combined, 35 plus 15 is 50, so 0.050 V final x. We know everything but V final x. So multiply these, add them together, keeping in count that negative, divide by 0.05 to solve for V final x, and what do I get? Positive 0.418 meters per second. This is a bigger velocity negative. Why did it end up positive? Oh, heavier mass. So heavy mass going to the right, lighter mass going to the left. So even though the lighter mass is going faster, apparently that one wins. All right, so there's my final velocity in the x direction. I'm going to do exactly the same thing in the y direction. So for the y direction, exact same equation. The mass of A, V, initial, A, Y, plus mass B, V, initial, B, in the y direction, equals the combined mass of my blob of clay, V final, Y. And here we go. We know the numbers for everything but V final Y. So I can solve for that. Mass of A, 0.035, V initial AY. A, V initial Y, plus 0.761, plus mass of B, 0.015, V initial BY, that one, negative 0.647, equals 0.050, combined mass, V final Y. And if you do the math here, you get V final Y, another positive, plus 0.339 meters per second. All right, now we're not done. We wanted to know the speed and the direction of the combined glob. We now know the component of the speed, left, right. We know the component of the, I should say velocity. We know the component of the velocity, up, down. We just need to slap those two together into a triangle. So that's what I'm going to do. I'm going to put these two into a triangle so that we can figure out the actual final velocity, speed and direction. I can get rid of this. So So this is using our trigonometry skills again, which you've used off and on through the whole class. So you should hopefully be getting a little more comfortable with them. All right, so what do we have for our final? In the x direction, we're going to the right at 0.418. And we're going up in the y direction. Okay, so 0.418 in the x direction, 0.339 in the y direction. I'll make this one a little bit longer since it's bigger. Those are my components. My final velocity is this thing right here. So this is my final velocity. And then we'll get our direction from that one. How do we do it? We know two sides of the triangle. We can figure out the hypotenuse and the angle. We will get that from Pythagorean theorem. So V final, a squared plus b squared equals c squared. Square root of 0.418 squared plus 0.339 squared. We get 0.54. This is my final answer, so now at this point I can round that down. So our speed is about 0.5 meter per second, but that's just our speed. We don't have our direction yet. We need our direction. And I know opposite and adjacent. That gives me the tangent. So the tangent of the angle is opposite over adjacent, which means if I solve for the angle, it's the inverse tangent of opposite over adjacent, 0.418. Solve that one, and you get, let's see, should be less than 45 because this is smaller than this, so 39. Ooh, still pretty big. And then we need to give the final answer more clearly than just that, because 39 degrees could be 39 degrees pointing in any direction. So when we give our final answer, we need to be very clear about what 39 degrees we are talking about. So there's multiple ways you can give angle answers. This question, the problem, gave us south of west or north of east. That is one way. Or you can just use the 0 to 360, 0, 90, 180, 270, 360. Our final answer, let's see, what do we have for our final answer? So the final velocity of the combined glob is 0.54 meters per second at, and now we're going above east. So the angle was 39 degrees north of east. Or if you wanted to use the 0 to 360, just put a plus sign. That one's easy. Yeah, plus 39 degrees. This is what the final answer should be. We were asked, what is the speed and direction of the combined glob? It's moving this fast, and it's moving in this direction. So we've answered it. Is it reasonable? Well, we had the first glob was moving at 1.8 meters per second, and the second at 2.5, but they were almost head-on to each other. So I can believe a smaller velocity. And then this one, it's heavier, so apparently it has more effect. This momentum is more important. I don't know how to call that. Which means that we continue, the combined glob goes up and to the right again. I think we've got the question answered. It looks like it's reasonable. So that is it. Okay, so that is a two-dimensional momentum collision problem. We can also do 2D problems where we have explosions, where we start with one object and it explodes into multiple pieces. We can do that in 2D. We can have bouncing off of each other in 2 dimensions as well. So we could have explosions where we start with one object, so initial is just one, and then in the final we have like one going here, one going there, maybe one going like that. Or we could have bouncing off, where instead of the two coming together and sticking, you might have one coming this way, one coming that way. They just barely collide. One might, for the initial, I'm making a mess here, final, the other might go like that. So this is just one of the types of momentum problems we're going to have, but 2 dimensions, all you have to do, separate out x, separate out y, Momentum is conserved in both directions. All right, that's 2D momentum. Good job.